Thank you for attending this session. Today, we're going to cover integer programming. So integer programming is an extension of linear programming. And if you remember in our last session, when we covered linear programming, basically for this problem, it was a minimum. So basically then we wanted to figure out what was the minimum point in our feasible region based off the constraints. And we found a minimum equal to 17.7. The minimum point occurred right here. X is equal to 1.38, and you can see that's what we solved here. Y is equal to 1.54, and that's what we got here. Those are the results from our linear programming. Integer programming says then that X and Y have to be integers. They can't be fractions. So for example, let's say then that we're looking at the cost of construction and how many, let's say that we use trucks and trains as part of construction. Let's say that X is equal to trucks, Y is equal to trains. When you solve the problem that you can't have 1.38 trucks, you can't have 1.54 trains. You either have 0 trains, 1 train, 2 trains, 3 trains, etc. In terms of the truck, same thing. 0 trucks, 1 truck, 2 trucks, 3 trucks, all the way through. That's the goal of integer programming. We need to determine the optimal values for X and Y, but they're limited to being integers only. They're limited to being integers only. X and Y can only be an integer. So if we look at these two graphs up here, so if we look at this graph on the left, if we look at this graph on the left, when we look at linear programming, the feasible region is the gray area. And I think right here they found that this and this right here was the, right here, that's the optimal part. This looks like it's a maximization problem. The feasible region, the area with feasible answers, can be anywhere in the gray area. So under linear programming, you can get an answer right here, and that would be appropriate. This, if I where I'm pointing, that looks like that could be 2.5 and 2.5. If I go right here, this will be 4.5 and let's say 1.25. I'm just eyeballing it. But if it's within the feasible region, if it's within the gray area, it's a feasible answer. Integer programming, on the other hand, both variables have to be an integer. Both variables have to be an integer. Therefore, they're going to fall within the gray area, but they have the additional constraints of being integers. So feasible answers are only these dots. Feasible answers are only these dots. So right here, what is a feasible answer? X is equal to 3, Y is equal to 2. And again, right here, this is in the feasible region. X is equal to 4, y is equal to 1. But they may not be the optimal answer. However, they are feasible answers. And again, under integer programming, the only feasible answers are the dots. The only feasible answers are the dots. Okay? Not everything in the gray area before. Again, we see here on this one to the right, the feasible region is the gray area. Right here, this was going to be the optimum if we had done normal linear programming. But those would have given us fractional answers. Those would have given us fractional answers. Again, what we want are integers. So like in this case then, the optimal answer, even though this is the best answer, this is going to maximize it, given that the answer has to be an integer. Let's see, what is this? 1, 2, 3, 4, 5. Okay? And then 1, 2, 3, 4, 5. So right here, the optimal integer answer, integer, is x is equal to 5, y is equal to 5. However, if you can choose this point that has fractional, that allows fractional values for x and y, you're going to get a better answer. You're going to get a higher optimum. However, if you have that constraint that x and y must be integers, then you can see circled in red here, this is the optimal answer. This is the optimal answer for an integer programming, which will be less than the optimal answer for a linear programming. The optimal answer for a linear programming will always be greater than or equal to the optimal answer for integer programming. So let's go back then to that problem we had done for linear programming. And again, we found an answer, x is equal to 1.38, y is equal to 1.54. We saw this both graphically and we used our solver to solve this numerically. Let's add the integer restrictions to x and y. Let's add the integer restrictions to x and y. So let's bring this problem down here and make this a little bit smaller and set up our solver. Okay, so you can see I have it, the basic setup here. The objective function, 5x plus 7y. There's the 5 for the x coefficient, 7 for the y coefficient. Constraint number 1, y has to be less than or equal to 4. That's right here. So we don't have to put any coefficient for x because there's no x in that constraint. Y is equal to 1, and you could see to the very right that the constraint, the upper level for the constraint, is equal to 4. In the next constraint, constraint number 2, 5x plus 2y, that's this line right here. That's this line right here. The upper limit to this the lower limit, because it has to be greater than or equal to 10, so the lower limit for this line is 10. Finally, we have this line here, x plus 3y, x is equal to 1. I have this listed as constraint number 3. X is equal to 1. The x coefficient is equal to 1. The y coefficient is equal to 3. The lower limit for constraint number 3 must be greater than or equal to 6. So we solved this as a linear programming before. Now let's try solving this as an integer programming. Previously, we determined that the answer was x is equal to 1.38, y is equal to 1.54. The minimum we can get is 17.7. The minimum objective value we can get is 17.7. However, we did not have, for the 17.7, we did not have the integer restriction on x and y. Now, let's introduce that restriction on x and y. They both have to be integers. So let's invoke the solver function. So data solver. Here's the dialog box. So we want to set the objective. So the objective is here. We want to minimize this. By changing cells, x, y, we want to set the constraints. So for constraint number 1, so we want to add, based off the results for constraint number 1, that has to be less than or equal to 4. That's this constraint right here. So that has to be less than or equal to, and we have this set up as 4. Let's add constraint number 2. So in constraint number 2, we have the result. This cell has to be greater than or equal to this constraint of 10. Let's add constraint number 3. So the result for constraint number 3 must be greater than or equal to, has to be a minimum of 6. So we see that constraint in this cell here. So those are all of our constraint equations. But now, how do we add the integer restriction to x and y? How do we add the integer restriction to x and y? So we have to add another constraint now. So we want to add. We want to cell reference x. Right here. In the middle of the dialog box, we're saying that x has to be equal to an integer. So you see there, int. Choose int in the dialog box, and you'll see then right here it says that the constraint is an integer. Let's do the same thing for y. So we want to add y in the dialog box here. In the middle, choose integer. Choose integer. So I think we've added all of our constraints. So let's hit OK. All right. So we want to set our objective C47, C44. See, this is wrong. So I got to set this objective C44. That's correct now, to a minimum by changing E44 and X. X is equal to E44, Y is equal to G44. You see, we have the integer restrictions on our variables. So X has to be an integer, Y has to be an integer, line 45 has to be less than or equal to 4. Constraint number 2, line 46, has to be greater than or equal to 10. I47, line 47 is the constraint number 3. That has to be greater than or equal to 6. We want to make all of our variables, X and Y, we want to make those positive. We want to choose. What solving method do we want to choose? We want to choose the simplex LP. Okay. So I think the dialog box is set up correctly. So let's hit solve, and let's see if we can come up with an answer. Let's hit solve. Okay. So right here, you can see then that our solver software determined the best answer, X is equal to 3. For Y, the best answer, Y is equal to 1. Y is equal to 1. And based on X is equal to 3, Y is equal to 1, we determined a value of 22. We determined a value of 22. So if we were going to look at X is equal to 3 and Y is equal to 1 on our graph here, it looks like, let's see, X is 1, 2, 3, Y is 1. The answer is about right here. The answer is about right here. So it's still in the feasible region. It's still in the feasible region. However, if we allowed X and Y to be fractional or decimal values, if we allowed X and Y to be fractional or decimal values, the minimum of the objective function, the minimum of Z, is equal to 17.7. However, if we put the integer restrictions on X and Y, you can see now that the best answer that we can come up with is 22. 22. So the first inclination is, you might say, well, why don't we just go out there and have, let's say x is equal, let's make x is equal to 1 and y is equal to 1. X is equal to 1 and y is equal to 1, and hit enter. All right, so we meet this constraint. We don't hit this constraint. 7 is not greater than or equal to 10. We don't meet constraint number 3. 4 is not greater than or equal to 6. So if we put a value of 1 right here, if you can see where I'm pointing on the graph, that's outside of the feasible region. That's outside of the feasible region, and therefore does not meet our requirements. And let's put the old answers back in. So we have 1.3, you have 1.38. Well, that's going to work. That's going to work. But there are no other values. What if we tried 2.2? Let's try x is equal to 2, y is equal to 2. We come up with 24. Remember that we came up with 22 before. So 2 is less than or equal to 4. 14 is greater than or equal to 10. 8 is greater than or equal to 6. But the value, and again, we want to minimize this value. The value that we determine when x is equal to 2, y is equal to 2, we come up with 24. That's about right here, right here. And when we determine the values of 3 and 1, when we determine the values of 3 and 1, we came up with a result of 22, which is better than 24. Again, we want to come up with the minimum answer possible. The answer of x is equal to 3, y is equal to 1. They meet all the constraints. They meet all the constraints. And 22 is lower than the 24 that we had in the previous iteration. So let's go back again to the dialog box. What were the additional constraints that we added when we used the solver command? It's these right here. E44 and G44 are integers. E44 and G44 are integers. So X is E44, Y is G44. To solve this as an integer programming problem, you have to add these constraints into the solver dialog box. You have to make X equal to an integer, Y equal to an integer. And the solver will return integer answers. Again, go down here and choose the simplex LP as the solving method. If we didn't solve this as an integer problem, the lowest value we can get was 17.7. 17.7. If we add the integer restriction, then the lowest answer we can get is 22. So the integer restriction gives us a less optimal answer than a straight linear programming problem. Okay? So the answer for a linear program, if we didn't put the integer restriction here, the answer for a linear programming problem will always be more optimal, at least as optimal as an integer programming problem. Why? Because the integer programming problem puts additional restrictions. The answer will still be within the feasible region, the blue area here. The answer will always be within the feasible region, but they just won't be optimal as compared to a linear programming problem. So that concludes this presentation then on integer programming. If you have any questions, please contact the instructor and watch the other videos that were given to you. Again, thank you for watching.